Okay, well, thanks a lot. I would like to thank the organizers for bringing me to this wonderful place. I have spent a long time in France, but I had never made it to Corsica before, so I'm delighted to be here. And so far, I have had a terrific time scientifically and otherwise. So yes, today I'm going to talk about how we can combine results of rigorous mathematical analysis and carefully design and executed numerical computations to learn something about some fundamental open problems in mathematical fluid mechanics. And I think that the sort of scheduling is perfect because I'm going to touch upon some of the problems that Bérengère introduced, more precisely the dissipation anomaly and also the question of finite time blow-up in hydrodynamic models. So I have to say that a lot of the work that I am about to describe is inspired by my interactions with this great man who unfortunately left us just over 2 years ago. So here's the plan of my presentation. So I'll basically cover two topics. The first topic is about the dissipation anomaly, but in 2D. So in turbulence research, we usually have results of two types. We have results which we think are sharp, but are not mathematically rigorous. Or we do have results which are mathematically rigorous, but they're usually not sharp. So this work is actually about a result that is both mathematically rigorous and sharp. So it's mathematically rigorous in the sense of rigorous analysis of partial differential equations, and it's sharp in the sense that it is given in terms of an upper bound that is demonstrably sharp in the sense that it cannot be improved. Okay? So this work was done mostly by my former PhD student, who is now a postdoc at KTH, Pip Mataru. Some of you here actually know him. And our collaborator, Tsuyoshi Yoneda in Tokyo, Japan. And the second topic I'm going to cover is this classical open problems in mathematical fluid mechanics concerning the possible formation of finite time singularities in Navier-Stokes flows. And I'll try to convince you that there are interesting things we can say about this problem by formulating it as an optimization problem. Okay? So the first part. So well, one of the key objects in turbulence research is energy dissipation. And the question that is often asked is what happens with this quantity in the limit of vanishing viscosity. So there is a lot of evidence, some of which was discussed by Bérengère. Here's another plot, indicating that when viscosity goes to zero, this quantity actually goes to a constant that might be greater than zero. So this fact has actually far-reaching consequences for sort of our understanding of the hydrodynamic models, because should this indeed happen, this would, among other things, imply that there's a finite time blow-up in the Euler equation, right? Because in order for this quantity to be finite in the implicit limit, when nu goes to zero, this quantity must be unbounded in a certain way, okay? Although there are well-respected researchers who argue that maybe the decay to zero is just very weak, perhaps logarithmic, so it is an open question. On the other hand, for the 1D Burgers equation, this question is actually understood completely. There's a very simple analytical construction that you can perform for a closed-form solution of Burgers equation, where you can basically compute the energy dissipation and show that in the implicit limit, it does indeed converge to a finite value, which is basically this quantity, where delta U is just the jump of velocity across the shock wave. So once the singularity hits, and we have we can only define a weak solution, then this weak solution starts to bleed energy at this rate. Okay, so this is a very simple example of dissipation anomaly in a 1D problem. And I'm actually going to come back to this problem later on, where I will make some comments concerning the irreversibility in this system. All right, so what about 2D? So let's set up the problem. So we are going to work on the 2D Navier-Stokes problem, defined on a periodic domain. We are going to focus on the vorticity formulation, with W representing vorticity, psi the stream function. Now in 2D, it makes more sense to talk about entropy dissipation rather than energy dissipation, because typically the flows are driven by the entropy forward cascade. So our quantity of interest will be this expression here, chi parameterized by nu, which will be considered a function of the initial condition in the problem. And one can show that dissipation of entropy is actually driven by this quantity, which we call the polentropy. just like dissipation of energy is driven by entropy, dissipation of entropy is driven by the next quantity, the quantity of the next higher order, namely palentropy. So the question I'm going to address in the first part of the talk is what happens in the implicit limit. So does the entropy dissipation go to a constant that would be greater than 0? So this problem, it turns out, has had a very interesting history. So I guess the first person to consider it was Batchelor, who in his theory of 2D turbulence assumed, incorrectly as it later appeared, that entropy dissipation does indeed go to a finite constant greater than 0. That was first questioned, as far as I know, by Tran and Dritschel, who around in the early 2000s argued sort of heuristically, but this was also supported by numerical computations, that the entropy dissipation should be bounded by this expression, so it should go to 0 sort of logarithmically. Okay, and more or less the same time, mathematicians including Anna Mazzucato, Helena Lopez, and Milton Filho actually proved rigorously that there can be no dissipation anomaly in 2D. Yes? Periodic. Periodic, well, so I'm considering periodic. Most of those results are either periodic or unbounded. Okay, so we do not consider solid boundaries. That's a good point. Solid boundaries definitely can change things. So even though there is no dissipation anomaly, it's a pertinent question how slowly entropy dissipation can vanish in the implicit limit. What is the slowest rate that, in the worst case, can characterize the decay of the entropy dissipation to 0? So our collaborator Tsuyoshi Yoneda with Jiang, they actually proved, it's a mathematically rigorous proof, that there exists a family of initial data which they constructed analytically, for which the entropy dissipation vanishes at least at this rate. So this gives us a lower bound. Okay, but the question is, what is the possible upper bound? Okay, so it turns out that this question is actually related to another problem of current interest, which is the following. So let's consider Navier-Stokes equation in 2D. So this is our Navier-Stokes equation in 2D with the written in the vorticity form, okay, with some initial condition, which I'll call phi. And then I'm going to consider an implicit version of this problem, so basically Euler problem in 2D, with the same initial condition given by phi. Okay? And the question, I can, in principle, can solve both problems. And the big question that is of a lot of interest to mathematicians is how the difference between the solutions of these two problems vanishes as nu goes to 0. Okay? So we want to be able to estimate the difference between W nu of t minus W of t, both corresponding to the same initial condition phi. We take some norm, let's say some phi, it's phi. Of course, sorry. Yeah. So we want to estimate this as some function of nu. So this problem has attracted interest from mathematicians, people like Claude Bachdos, Ed Ristiti, and Peter Constantin for many, many years. And there have been many, many results. However, what we did in our paper was to recognize that there is a connection between this problem and the problem of dissipation anomaly in 2D. Namely, you can rigorously estimate the entropy dissipation in terms of something related to the initial condition and basically this quantity. So if you have an upper bound on this quantity, which is the difference between the solution of the viscous Navier-Stokes and the implicit Euler equation, then this upper bound will apply a bound on the entropy dissipation. Okay? And as I said, this latter problem has attracted a lot of interest. There have been many, many results, culminating with this result that was achieved a couple of years ago, which provides arguably the sharpest available to date bound on this quantity. Okay? So it gives us an exponential function of viscosity nu with some exponent and constant, which both depend on the length of the time window. And I would like to stress is that the dependence of this exponent on the length of the time window is exponential. This is going to come back. Okay? So this estimate implies an upper bound on entropy dissipation. So this is, an estimate that could or could not be sharp. So we would like to know if this estimate is sharp in the sense that it could be realized by actual solutions of Navier-Stokes flow. Okay, if not, then it can probably be could be improved. So how can we do this? Well, we are asking ourselves the question. So, given the length of the time window and some fixed viscosity nu, what is the largest possible dissipation entropy that can be achieved under 2D Navier-Stokes dynamics? Okay, so this brings us to the following optimization problem. We are going to study this problem systematically using methods of mathematical optimization by solving this problem. So we are looking for an initial condition that has to belong to some Sobolev space H1. I'll explain why this needs to happen in a moment. Zero mean with a fixed initial polystrophy such that it will maximize the entropy dissipation on some fixed time t. Okay, we do need this constraint because in the absence of such a constraint, we could maximize the entropy dissipation just by maximizing the size of initial data. So we have to somehow constrain the initial data. Okay, and the initial condition must be in Sobolev space H1 because otherwise those quantities would not be well defined. Okay, so our goal is basically to solve this problem numerically in the limit of vanishing viscosity, to see whether the behavior, the worst case behavior that can be generated by solutions of this problem realizes the estimate that we have just found. Okay, and we are going to do this. There are 3 parameters in the problems. We are going to do this for a fixed initial for a fixed size of initial data. We'll set initial polystrophy equal to 1 for different t, and for different values of viscosity that will go to 0. Okay. How do we solve such problems? So here I'll connect to a lot that has been discussed in this meeting, namely gradient flows that are traditionally used to find ground states in quantum fluid mechanics. So we are solving this problem using a suitable gradient flow, where the key element here is the gradient of the objective functional, which is the entropy dissipation, with respect to the initial condition. So this is an infinite dimensional object that characterizes how the entropy dissipation depends on the initial data via solutions of the Navier-Stokes problem. Okay, it's a Riemannian problem because the solutions have to be defined on a manifold. So we need a retraction. We can also add a projection here. Tau n is a time step, and phi 0 is initial guess. So how do we solve such problems? So in some ways, it's similar to what is done in quantum turbulence, and in some ways, it's different because now we have a time evolution. So the gradient is not just a differential expression based on the functional, but we do need to account for the evolution, which is done by solving the so-called Edring system, which is actually an interesting animal because for evolutionary problems, this system is actually solved backwards in time. Okay, and when we define this Edring system properly, this allows us to compute the gradient of the objective functional in the space L2, and then using the tricks that Jono described, we can compute the corresponding H1 gradient. Because this gradient flow is defined in an infinite dimensional space, which is H1. So it's absolutely necessary that the solutions be constructed in that space, and this is what we need. It's not a matter of numerical convenience. It's a matter of having a well-posed mathematical problem. Okay. So the Edring-based machinery has been around for perhaps a quarter of a century, which is not to say that it is easy to implement, but it can be done when you have a talented graduate student. So here's what the algorithm looks like. Well, we start by fixing the values of the constraints, P0 and T and nu. We start with some initial guess. And then we first solve the Navier-Stokes system forward in time. Then we solve the adjoint Navier-Stokes system backwards in time. These 2 solutions allow us to compute the L2 gradient. Now from the L2 gradient, we compute the H1 gradient. And then we use the H1 gradient to update our approximation of the optimal initial condition while respecting the constraint. And we iterate this loop until convergence, meaning that the relative increase of the functional drops below certain tolerance. So here are the results that we obtained. So this is a non-convex problem. So in principle, it admits non-unique local maximizers. And we have indeed found 7 distinct branches. Here is what the initial conditions look like. Here is what the polystrophy evolution looks like in those different branches. Here is the structure of the vorticity field during at the instant of time when the polynstrophy achieves a peak value. So I actually have an animation. Hopefully it will run. So you see that in all cases, the maximum entropy dissipation is realized by generating those very thin filaments. And the difference between different branches is how those filaments are packed into the periodic box. And something that I find remarkable about this result is that situations where the initial conditions are almost identical actually can result in very different final states, as happens for branch 2 and branch 3. Let me run it one more time. So take a look at branch 2 and branch 3. They are almost indistinguishable in terms of initial conditions, yet the resulting flow evolutions are actually quite different. So this is basically what realizes the worst case scenario in terms of entropy dissipation in 2D. Okay? All right. So let's take a look at this from a more quantitative point of view, because after all, we are after our estimate. Yeah. So this is the entropy dissipation as a function of the length of the time window obtained for different viscosity values, where we see those 7 branches. Okay. So we are interested in our estimate. So we basically have to compute an envelope of our different branches for each viscosity value, which gives us this. Okay. So now the question is how this worst case behavior compares to our estimate. So what we are going to do is we're going to fix time and then look at the slices of those plots corresponding to decreasing vorticity values. And here is what we get. So we basically on this plot, I'm showing these values normalized by the form of the estimate, where the exponent and the constant have been fixed with the least square fit. And you see that when you do the fitting, that estimate actually matches the true behavior very, very closely, because the deviation is literally on the order of a few percent. So basically, the fact that the actual behavior of the entropy dissipation for different values of t matches so well is matched so well by this estimate demonstrate that this estimate is indeed sharp. Furthermore, when you plotted the exponent alpha of t as a function of t, the length of the time window, the trend actually follows an exponential, which is precisely what the estimate predicted. Okay. So yeah, so this brings me pretty much to the end of my part 1. So we consider the the implicit limit of the entropy dissipation in 2D flows. We solved a family of PD constraint optimization problems to determine flows maximizing the entropy dissipation for different lengths of the time window and different dissipations. Found 6 branches of locally maximizing flows, each revealing a different mechanism for the entropy dissipation. And most importantly, the dependence of the maximum entropy dissipation on mu saturates an a priori estimate given in this form, including exponential dependence of the exponent, demonstrating that this bound is sharp. It cannot be improved. So in some sense, that's the end of the story. The problem is solved. I mean, we cannot produce a better estimate because that one is really sharp. So an obvious question is, well, what happens in 3D? And that's something that we are starting to look into, how to construct a similar optimization problem that we could solve in 3D. And needless to say, because that's an open problem, there are no a priori estimates available in the 3D case. So this marks the end of part 1. Maybe I'll pause briefly to see if there are perhaps any questions or comments. Yes, Bérangère. Uh-huh. 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 Yeah. 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 Well, okay. For t going to infinity, the dissipation will go to 0, obviously. But So no, but we are in. So, okay. So sharpness of an estimate is defined by the fact that the estimate predicts the observed behavior when a certain parameter is varied, while others are fixed. So what we did, yeah, but no, but what we did here is the opposite. We actually fixed time, and then varied viscosity, because that's how. Yeah, I mean, okay, so yeah, okay. I cannot say that the estimate is sharp with respect to t, but it seems to be sharp with respect to nu. But this is the principal question, because this is what the dissipation anomaly is about. Having said that, the fact that the decrease of the exponent in this upper bound follows an exponential trend, which is pretty much what we have in the a priori estimate, seems to indicate that it might be sharp with respect to t as well. Although this was not the primary sort of concern in this study. But you're right. I mean, we have estimate that involves several parameters, and they might be sharp with respect to some, while not being sharp with respect to the other ones. Here, because this is a question about dissipation anomaly, we are interested in sharpness with respect to nu. All right. So do I have your green light to go to the? Yes. Sorry.
In this framework, there is the famous Kreisstein theory of entropy cascade.
Yeah. Yeah.
And what I remember from many years ago is that the typical structure that dissipates entropy is a pileup of vortex sheets. Okay? So in fact, if you start with only large scales and move forward in time, you first get k minus 4 by having single discontinuity lines of the vorticity. And then if you wait long enough, when the balance trophy saturates, you typically see pileup of vortex sheets. So I was wondering, that's my question, is the thing that saturates your inequality, are they pileup of vortex sheets? They are. Okay.
Yeah. Yeah. Sure. Yeah.
It's equilibrium solution or stationary solution of Euler are characterized by omega equal f.
Yeah, like an elliptic boundary value problem. Yeah.
And do your solutions satisfy this?
I don't think so. I don't think so, because they are time dependent. They are time dependent. That is only for time independent. Yeah.
But actually, it's pileup of vortex sheets superimposed with the strain. That is.
Yeah. Well, the flow has to sort of arrange itself in a strategic manner. Yeah. So which mechanism wins depends on parameters, viscosity and t. But one way or another, you always have some form of pileup of vortex sheets. Yeah.
So all solutions are zero mean.
Zero mean. Yeah. Which is an invariant. Is it important? I don't think so. It's just a technical thing.
Is technical for the estimation?
No, it's actually not, because Laplacian is not reversible, invertible if vorticity is not zero. So there can be some issues. Anyways, on to part 2. Okay, part 2. Yeah, so here we are going to use sort of similar methods to systematically search for worst case and possibly singular behavior in Navier-Stokes flows. So again, Navier-Stokes system, except that now we are actually going to focus on the real problem in 3, but again, we are going to stick to the idealized case with the periodic boundary conditions. So the big question is, if we start with a smooth initial condition, as smooth as you wish, does the system admit a smooth solution for arbitrarily long time? And unfortunately, the answer is not. I mean, we don't know. And this is very disappointing, because solutions which are not smooth are not really physically meaningful. So as you probably know, this question has been identified as one of the 7 millennium problems posed by the Clay Institute as challenges for mathematicians in the 21st century, with a suitable monetary prize of $1 million. So since this is summer school, I'll have some more general kind of comments about singularity formation, and then I'll also make some additional comments about irreversibility that is kind of related to this. So what could go wrong with solutions of Navier-Stokes system? Why could there be a singularity? So let's consider the vorticity form of the Navier-Stokes system. Now in 3D, we have the vortex stretching term. So velocity is obtained from vorticity using the Biot-Savart kernel, which can be written in the form of this singular integral operator. So using the Biot-Savart kernel, we can write the Navier-Stokes equation, or Euler equation if we drop viscosity, in terms of vorticity only, which clearly shows that this is a quadratic equation. Okay? However, this quadratic term is kind of tricky, right? Because there's a gradient, there's the convolution. So what could the fact that this is a quadratic equation imply in terms of existence of solutions? Well, let's take the simplest example possible, namely, one-dimensional ODE, which is quadratic, right? So what do we know about the solution of this problem? I mean, we can solve it right away. This is a first-year calculus example. We have the solution, and the solution becomes unbounded. If we start with positive initial data, the solution becomes unbounded in finite time. So we have a blow-up in this very simple problem, okay, which admittedly does have some similarity to Navier-Stokes. So clearly, this solution is not satisfied at t equal to 0, and it's not defined for larger times. So what can one do to compute the solution for larger times? This is actually a very tricky question from the mathematical point of view. So let's consider a slightly more involved problem, which is closer to fluid mechanics, namely Invisit-Burgers equation. So we can actually solve Burgers equation using this implicit formula. And then when you look at it carefully, you will see that the solution will develop unbounded derivatives at the time, which is given by this expression. And this is basically what happens. If we start with a very simple initial condition, just a sign, in finite time, the solution develops an infinite gradient at the origin. Okay, meaning that the solution is not satisfied at the time t equal to 0. However, using the machinery of weak solutions, which is, in my opinion, one of the biggest inventions of applied mathematics of the 20th century, we can actually define a mathematically meaningful solution for larger times. Okay, so those solutions are defined in a weak sense, which is defined in terms of integrals and test functions, and they may not, and in some cases will not, satisfy the original form of the Burgers equation. So what does it have to do with irreversibility? Well, there's actually a very close connection between singularity formation and irreversibility, and I think that the Burgers equation is a perfect model to illustrate it. So since I just wanted to add this following Béranger's lecture, so I don't have this in my slides. So let's take a look at, again, Invisit-Burgers equation with initial condition given by a sign. Okay, so the way we solve this equation, we go to the characteristic representation, where we basically convert it to an infinite family of ordinary differential equations, which we can solve. And then the solution looks like this. So this is space, and this is time. And what I'm drawing here are isolines of the solution obtained using the characteristic equations, corresponding to the initial condition given by a sign. So we basically have two fastest moving characteristics, one moving from the maximum here, and another one moving backwards from the minimum here. And at some point, they unavoidably collide. At which point, this is where the infinite gradient develops, and the solution is no longer satisfied in the classical sense. However, we can continue the solution as a weak solution. Okay. However, as long as the solution exists in the classical sense, we can always reverse time, and we can move back along the characteristics. However, as soon as the characteristics have collided, we can no longer do this, because there's information loss that occurs when the characteristics collide. We cannot undo this fact and move along the characteristics in the backward time once the singularity has occurred. Okay, so there is inherent loss of information that occurs when characteristics collide. So, well, one could in principle define the characteristics like this, but there is infinitely many ways of assigning initial data to the problems that would go backwards in time. So the backward problem is fundamentally non-unique if you want to move backwards in time from the time after the Armageddon has occurred. Okay? Oops, what is that? Sorry about it. Yeah, whatever. Okay, so the big question, okay, half an hour. So the big question is, could something like this happen in the Navier-Stokes system? Who cares? Well, I mean, if the solutions become singular, then Navier-Stokes is not a correct model for viscous incompressible flows, period. And as such, would need to be amended in one way or another, right? Because in natural sciences, we want to work with well-posed models, such that if you start with good initial data, you should be able to integrate them in time until basically infinity. So if a singularity is possible, this means that the model does not represent physical reality. Okay, so that's why we use Navier-Stokes to do all kinds of things, from designing space flight to designing drug injection strategies and whatnot. Okay, so let's see. I'm going to review where things stand from a mathematical point of view as of now, which basically hasn't changed for the last 70 years. So in 2D, existence is pretty much complete. So we know that smooth and initial solutions exist for arbitrarily large times and arbitrarily large initial data. So the problem is pretty much closed. Now in 3D, the situation is fundamentally different. Namely, only weak solutions, which are defined in the integral sense and are possibly non-smooth, can exist for arbitrarily long times. Classical solutions, which are smooth, there's a typo here, I'm sorry, have been proven to exist for finite times only. Okay? Nobody has been able to prove that those solutions would blow up, but nobody has been able to prove that it will not occur. So the possibility of blow up, namely finite time singularity formation, has not been ruled out. So this is fundamentally a problem in mathematical analysis. However, here I will try to sort of argue that we can learn about the sort of mathematics of this problem by performing carefully designed and carefully executed numerical computations, okay, in a special way. So in mathematics, the mathematics of these problems typically revolves around the so-called conditional regularity results. These are conditions imposed on the velocity fields, which we don't know if they are true, but if they were to be satisfied, they would imply that the solution is smooth and therefore satisfies the equation in the classical sense. So arguably the best known result of this type is the so-called entropy condition, which focuses on this quantity, which we all like, namely the entropy, which is L to norm of the vorticity, which basically says that the solutions remain smooth. To be precise, they live in a certain Gevrey space, as long as the entropy is bounded. And that's an if and only if statement, which makes this a very convenient tool for monitoring the regularity of the solution. Okay? Should there be a singularity in the Navier-Stokes law, the solution is not going to blow up a derivative at a time. All derivatives up to the first one must blow up instantaneously. Okay? And that's a quadratic quantity with a very sort of intuitive physical meaning. So that's why it's so good. So basically the question is, if we start with an initial condition that has fixed entropy, can it happen that under Navier-Stokes flow, this quantity would blow up in finite time? Well, I mean, mathematically, when you look at this, we would like to come up with estimates on the rate of growth of entropy, d dt, which has been done by mathematicians. And those results typically have this form. So the rate of growth of entropy is typically upper bounded by some constant c, and the entropy itself with some exponent alpha, which depends on the dimension. So when you look at this equation, then in the context of what we said about this toy model in 1D, one might be tempted to think that as soon as alpha is greater than 1, the solution will blow up. That is actually not quite the case, because we actually have another player in this game, namely we have the kinetic energy, where the right-hand side, namely its dissipation, is characterized by the entropy. So when you integrate this equation in time, you obtain basically an upper bound on the time integral of entropy, okay? Which, when one uses Gronwall's lemma with this inequality, allows us to basically a priori upper bound 1 power of entropy. So we are basically getting 1 power for free, which means that entropy will be bounded for all times as long as the exponent is actually less than or equal to 2. So in this talk, you will see there are many inequalities. So mathematicians like inequalities, probably even more than we like equations. And I guess the reason is that in the pursuit of sort of worst case scenarios, which is what mathematical rigor is all about, inequalities allow us to look at whole families of solutions rather than just on one particular solution. So you will see a lot of inequalities here. However, when alpha is greater than equal to greater than 2, then there is no a priori finite bound on entropy. So in 2D, the form of this estimate, I told you that the exponent depends on the dimension. So in 2D, this exponent is exactly 2, which is the borderline case. So again, using the Gronwall's lemma, we can prove that the entropy is bounded globally in time, which in turn implies smoothness of solutions at all times. So this is how we prove the existence of solutions of classical solutions in 2D. Now in 3D, the situation is completely different because the upper bound is proportional to the power 3. Okay? And the best we can do is just integrate this inequality, this inequation, as Charlie Darling used to say, which will give us this upper bound, which, however, is itself unbounded, right? Because for a certain time, this thing will blow up. So this is actually, these are the sharpest estimates available to date. Yet, based on those estimates, we cannot really rule out singularity in finite time. Okay? So this was one, perhaps the most popular and well-known conditional regularity result. There's another one that has played a significant role in mathematical fluid mechanics, the so-called Ladezhenskaya-Prodi-Serin family of conditions. So what those conditions assert is that if the solution of the Navier-Stokes problem lives in this function space, so basically the pth power of the LQ norm is finite, when P and Q are related by those inequalities, then we know that the solution is smooth and satisfies the equations in the classical sense. And there's also an important limiting case where Q is equal to 3, which says that the L3 norm must be bounded for the solution to be true in the classical sense. So this is actually a very subtle problem for the following reasons, and this also concerns how we approach this problem from a computational point of view. So I have some comments about the nature of possible blow-up. So let's assume that the solution does blow up at some time t0. So what the entropy condition implies is that, well, the entropy must become infinite at that time. However, we also know that the integral of entropy must be finite, because this is basically upper bounded by initial energy. All right? So if there is blow-up, then it must be a very subtle phenomenon, such that this quantity will go to infinity slowly enough so that its integral will remain finite. Okay? And the same thing happens with the Ladezhenskaya-Prodi-Serin conditions, except that they are more complicated. So if there is blow-up at time t0, then this quantity will go to infinity. However, we also know, we have a priori estimate for an Navier-Stokes system, that this quantity, where the exponent here is roughly half of that one, will be finite. Okay? So the singularity must be weak enough so that this will blow up, but this will remain finite. Okay? So this provides constraints on what can happen in the worst case scenario, demonstrating that the blow-up is actually a very subtle nature. Okay? It's actually very weak. It's not such a massive explosion as happens in the inviscid burgers, for example. All right? All right, so this is, this was mathematical analysis, so where do computations come into play? So it was, as far as I can tell, it was Charlie Daring who was the first person to pose questions about the sharpness of those estimates as a mathematical optimization problem. So what he did with his student Lulu was to look at this estimate. The question is this estimate sharp in terms of this exponent? Okay? So they formulated and solved the following optimization problem. So they were looking at the solenoidal vector field in H2 that would maximize d dt, so the rate of growth of entropy, subject to this constraint. Okay? Where d dt using Navier-Stokes can be expressed using this quantity, either is a parameter. So there is no time evolution. We are just looking at the problem instantaneously. What is the, it's a kinematic problem. What is the vector field with fixed entropy that has the biggest oomph, where oomph is measured by this quantity, okay? So, yeah, they actually solved this problem using a gradient flow 15 years ago, and this is what they obtained. So basically what they did was they would fix E0, solve this problem, and then obtain the maximizer, then compute d dt, and then increase the value of E0, and so on. So here is the maximum obtained value of d dt, and here's the entropy. And you see that the slope is very close to 3, demonstrating that the vector fields they found actually saturate the instantaneous estimate. meaning that that estimate cannot be improved by lowering the exponent. Perhaps it can be improved by lowering the prefactor, but not the exponent. What do those fields look like? Well, they are two colliding vortex rings. Okay? So why doesn't this solve the whole problem? Well, this does not solve the whole problem, because if you use these guys as the initial condition for Navier-Stokes problem, then the nonlinear growth is immediately depleted. Okay? You do saturate the estimate instantaneously, but then very little growth of entropy is achieved in finite time, as showed by those results. So basically, you grow the entropy a little bit, and then it decreases. And basically, what happens is that we have those vortex rings sort of approaching each other and then spreading away, and basically nothing happens. Okay? However, instantaneously, they produce as much Paulin's entropy as is mathematically possible. Yes?
How it comes that you get vortex rings after the minimization? You start from something that looks
Yeah.
like a vortex ring?
No, I mean,
Just you put random ways, the random way.
that's actually a good question. So what you do, there's a systematic way of doing that, which kind of mimics what people like Yonut do and Weizu in quantum turbulence. You solve the problem in the limit of epsilon going to 0. I actually might have some comments about it. I think... no, I don't, sorry. So I'll explain it now. So you basically solve the problem in the limit of E0 going to 0, which means that the cubic term goes out, and you end up with the problem that has a quadratic objective functional with a quadratic constraint, which can be solved using Lagrange multipliers, which basically boils down to an eigenvalue problem for a vector Laplacian. And then use these guys to seed the branches, and then you can follow the branches.
And these lower branches contain vortex ring?
Well, they are cellular, because they are eigenfunctions of the vector Laplacian. But when you increase E0 and do continuation with respect to E0, they eventually morph into vortex rings, yeah. Interestingly, one of those limiting solutions obtained when E0 goes to 0 is the Taylor-Green vortex that has been used for decades in this business. And I think it's kind of interesting that it arises as a special case in this variational formulation. All right, let's see, where were we? Okay, so some comments. So what we learned from that problem is that for blow-up to occur, we probably cannot use extreme vortex states, which saturate the instantaneous estimate. So obviously the flows related to the vortex rings, which basically have zero swirl, they must be smooth. They are globally well posed. There are results saying that axisymmetric flows with no swirl are globally well posed. So what this is telling us is that should blow-up occur in our Navier-Stokes system, it must be associated with initial data such that does not saturate the instantaneous estimate. And the way to look for such sub-extreme states is to solve an optimization problem over a finite time window. And this is what we are going to do now. So we, motivated by the two conditional regularity results, we have formulated two optimization problems. One where we fix T and this initial entropy, and we seek an initial condition that will maximize the entropy at the final time, again subject to the Navier-Stokes equation. This problem is basically a 3D version of the entropy dissipation problem I discussed earlier. So this is a PDE optimization problem from hell, but one can solve it if one has resources. And there's another problem where we take the one of the Ladygensky-Prodi-Serrin criteria. We took one with Q equal to 4 and P equal to 8 and maximize this quantity. So here things become subtle, right? Because when you look at this problem, a natural constraint would be to fix the L4 norm, okay? And that's what we do. And it would be a natural thing to do to look for solutions in this function space, in L4. However, L4 is not a Hilbert space. And those of us in the business of computing gradient flows know that those approaches are nicely formulated in a Hilbert space, because as Yonut explained, we need the Riesz theorem to compute the gradient. So here we have a situation where we don't have Hilbert structure, and what to do. So I think we have some ideas how to solve, and I'll be happy to talk to interested people offline. But what we did here, we actually formulated the problem in the largest Sobolev space with the Hilbert structure that is embedded in L4. So it's a kind of technicality. All right, again, how do we find those solutions? So gradient flow with the gradient of the objective functional computed using the adjoint system, looping, and so on. Adjoint system, yes, this is the Riesz theorem in L2, in H1. So these are basically technical details. Let me focus on the results. I think this is more relevant for this group. So here is the entropy in the extreme flows obtained by solving problem 1. Red is finite time optimization with different lengths of the capital T, optimization over different time windows. Blue is the evolution of entropy corresponding to the two vortex rings, which are instantaneous maximizers found by Charlie Daring. Okay? And you see that instantaneously, the two vortex rings indeed win. However, the growth of entropy is instantly depleted, giving us very little in the end. On the other hand, when we solve the finite time problem, we do get much more growth. Okay? This is what the optimal initial conditions look like. These are the instantaneous maximizers, the two vortex rings, which, by the way, become smaller and smaller as you crank up entropy. We found two branches of solutions. And the main difference is that those flows, the initial conditions, are not localized anymore. They actually fill the domain almost fully. So here, summary of the main results. So here so each symbol on this plot represents the maximum attained value of entropy for a given t for branches characterized by E0. And there was lots of computational time burned to obtain those results. Typically, one computation, one symbol required hundreds of hours on hundreds of CPU on some of the biggest computers we have in Canada. So we see that for each E0, there's a well-defined maximum. And it is interesting to happen with the maximum entropy obtained over all times as we increase E0. So this is basically answers the question, what is the largest growth of entropy we can generate? And when we plot those results, we see a very clean power law with an exponent almost 1.5. This is what the initial condition looks like. Interestingly, we see that it has the form of three perpendicular pairs of anti-parallel vortex tubes. And I have an animation that shows the flow evolution. Oh, sorry, that's not what I wanted to. So as time goes on, you will see the emergence of a basically kind of turbulent tangle. It's basically a turbulent flow, and actually it does have a modest Kolmogorov type spectrum. I mean, it's a Kolmogorov type spectrum, but over a rather small range of wave numbers because the resolution is not very high. Vorticity, so each color corresponds to different Cartesian component of vorticity. So Wx, Wy, Wz. So this is basically what the worst case scenario in Navier-Stokes looks like. This is what saturates, well, this is what realizes the worst case growth that we could find. So remember that in order to have, for blow-up to occur, entropy must be amplified in a sustained manner at the rate that is at least proportional to itself in the power 2. So to check that, here we plot the rate of growth of entropy for different optimal flows versus E. And we see that the sustained rate has exponent even less than 1. And we need 2, for blow-up. Which means that even in this worst case scenario, we are light years away from being able to generate singularity. Okay, so something quick about the Lagrangian-Sky-Prodi series. So we basically repeated this exercise for problem 2, and found the substantial transient growth of the L4 norm. Here case as well, we did not find any evidence whatsoever for finite time singularity formation. This is what the optimal flows look like. This is initial condition. This is the final state. I also have an animation illustrating what is happening. So you will see that here the behavior of the flow is completely different. It's very localized. While for the entropy condition we had this turbulent mass filling the periodic box, here it's two vortex rings that kind of evolve and deform each other. However, when we for the solutions of the of problem 2, focus on the Latyszenska-Prodi-Serrin criterion, we can also compute the entropy, the maximum entropy and the initial entropy. And when we plot this, and then take the envelope, we also obtain an envelope that scales with an exponent of 3/2, which suggests that there seems to be something universal about this. Okay, so I guess this brings me to my conclusions. So, well, no matter what we did, there was no evidence for singularity formation in Navier-Stokes flow. That said, we do not know if the maximizers are global. This is a non-convex problem, so it's always possible that we may have missed some local maximizers. For the entropy and the Prodi-Serrin problems, we found completely different mechanisms for extreme growth. However, they all resulted in the same power law dependence of maximum entropy only 0, which, by the way, was the same as what we found by solving this problem for Burger's equation, in 1D Burger's equation 15 years ago. Some ongoing problems. Euler, we do have a preprint on arXiv showing that there might actually be a singularity in Euler that is found in this way. Let's see. I would like to leave some time for more questions. There's a question about what happens if we consider problems with stochastic excitations. Is this stochastic excitation going to conspire with the nonlinearity to create blow-up, or maybe regularize it? We are also working on that. So what I just described is a summary of a 10 years worth of research on related problems, where in addition to 3D Navier-Stokes, we also considered similar energy estimates for 2D Navier-Stokes and 1D Burgers. Even though we know there's going to be no singularity for 1D viscous Burgers or 2D Navier-Stokes, the question if those type of estimates are sharp is actually quite pertinent, because they are obtained using the same mathematical tools as the estimates in 3D. And paradoxically, the situation in 1D is actually less satisfactory than in 3D, because some of the fundamental estimates in 2D that we have in 1D are in fact not sharp. Some references, and yes, so recently with Charlie Daring, Jean-Luc Tuffaut, and David Goluskin, we edited a special issue of Philosophical Transactions of the Real Society, and I wrote a review paper that summarizes the work on the systematic search of extreme and possibly singular behavior, so it might be interesting to take a look at that. With this, I'll stop. Well, thank you for your attention. I'll be delighted to answer any questions. Thank you very much.